So actually I had to look up what .NET Southwest was, because it had South Space West, and we actually have a Southwest in the States, but it's just one word. So I didn't actually know it was this whole region in England. I've never actually been to Bristol. I have been to Bath a couple times, and everyone I met in Bath said there was no reason to visit Bristol. So just FYI, they don't think that much of you over there, I guess. So yeah, thanks for having me, everyone. My name is Jimmy Bogard. You can find me on Twitter at @jbogard. And this presentation you can find on my GitHub at github.com/jbogard. And I blog a lot about this topic and others on my blog at jimmybogard.com. Just a little bit about me. I've been receiving the Microsoft MVP Award, I guess, for doing these kinds of things. They don't really tell me why. I work at a company called Headspring, although right now I'm working there in contracting. And now I've gone my independent way. And I do a lot of open source. So some of those projects you may recognize, some of them you may love, some of them you may hate. I've also heard that as well. But everything I do, I try to give back and put out there out in the public so that others can learn from the things that I've been able to do on the projects that I've been on. But in terms of my experience, I've been doing independent consulting, or I've been doing consulting for about 12 or 13 years now. So a lot of what we'll be talking about in this presentation are a lot of my experiences building distributed systems over that time. For the early part of my career, though, I didn't really have to worry about any kind of distributed systems or communications. Like, the things I was doing were really just kind of interior applications. I have a web app or a desktop app, and that thing talks to a database, and then really all I have to do is really just manage the complexity of how big that application gets. I did dabble a little bit in distributed systems early on in my career, but that was not a whole lot. It was mainly for like asynchronous background jobs, but nothing too complicated. But one of my first very big projects when I joined Headspring was a system which basically there was zero user interface except for like a customer service portal. But everything else was all this background stuff going on. And so I had to have basically a crash course in understanding, well, how distributed systems work, how asynchronous communication works, and how we can build complex interactions building on top of these kind of lower level communication primitives. So I wanted to talk about microservices because microservices seems to be dominating a lot of the conversation in terms of distributed systems these days. And no matter what kind of architectural style you pick, eventually you will come to the point where you will have systems talk to each other. And once you get to the point where you have to have systems talk to each other, then you have to look at, well, what is the nature of that communication and how should those systems actually talk? Before we get too far, though, I do want to define first my interpretation of what that term microservice means, because the original definition I found was a little bit lacking in terms of clarity. Like, it's hard to explain to the business like what a microservice was and why they should be doing it. So I tried to refine a little bit just for my own purposes. And to say that a microservice is a service, like a service-oriented architecture, where I'm focusing my design towards the smallest autonomous boundary. And instead of thinking about things in terms of micro being a number of lines of code or set of functionality, service-oriented architectures are all about building up systems that have this property of autonomy. And autonomy just means like they can stand on their own. They are responsible for their own data. They're responsible for their own uptime. They're responsible for their own behavior and their own security. They can do everything by themselves. And this idea of microservices is saying, well, what if we try to make those boundaries as small as possible while still preserving that property of autonomy? So I do read a lot of stuff about microservice architectures gone wrong. And a lot of times, the reason why I see those architectures go wrong, or it's really two reasons why. First of all, they make the boundaries way too small. And so they're just kind of taking individual classes and functions and saying, well, that's its own service now. And the overall architecture doesn't look any different, except all the arrows are now like HTTP calls. And the other reason why I see these kinds of architectures fail is not really thinking about the communication of each individual service to another, and not really thinking about the possibilities of how services can communicate, to make sure that they're choosing, when services need to collaborate on something, that we're choosing the right communication pattern for the job. And so for me, when I approach a a microservice, a project and microservice-based system, I look at all the patterns in my tool belt as possibilities of ways things can communicate, and then recognizing that each pattern has its own benefits and drawbacks, its own positives, negatives, its trade-offs, and understand that I really need to pick the right pattern for each job and not just say all services need to communicate via this or all services need to communicate via that. So when we talk about microservices as always having to do like REST-based communication or RPC, those tend not to succeed because if we see those kinds of systems realized in the real life, we recognize very quickly that us in the real life will choose different kinds of communication for different jobs. And so that's where I really like to ground my thinking when I'm picturing systems and services talking to each other. As I imagine, if I took each of these systems and services and made each of the systems and services an actual human being, then how would those human beings in real life accomplish whatever task they're trying to perform? And if that job is accomplished well in real life, there's a very good chance that that communication style will work well in the distributed life and the computing life as well. So I want to look at if we take a single monolithic application, what does that look like in the real life? In the real life, a single monolith is a person that is doing every single job of an organization. And if I want to take that one person and try to scale that one person up, then I have to start splitting out responsibilities of what that one person is doing. And once I start to split out those responsibilities, each individual new person becomes autonomous. They're doing their own job that they've been assigned to. And then when we have to accomplish something as a group, then we have to have some kind of communication strategy to ensure our overall job gets done. So I wanted to walk through an example that I see in real life of taking some individual kind of system that involves multiple people and then seeing how that translates out into the real world. So taking those kind of human-based architectures and saying, well, how does that translate that into actual distributed systems that we might build? So I'm from Austin, Texas. And if you don't know, Austin, Texas is a very hipster kind of city. And hipster kind of cities have these things known as food trucks. And food trucks are really this like completely self-encapsulated restaurant that can drive around and deliver food wherever they drive. And so in Austin, before I had to stay home all the time because of COVID, the office I was at had food trucks that would come every single day. And on one of the days, I think someone needs to mute. That's another bingo check, by the way, for someone needs to mute. So one of the trucks that comes as part of that is a hot dog food truck. And this hot dog food truck has, of course, like every hipster food truck, has some kind of twist on it. And its twist is not just regular hot dogs, but it makes bacon-wrapped hot dogs, streaky bacon, not proper bacon. And not just bacon-wrapped, but it also takes that bacon-wrapped hot dogs and deep fries it. So that's its claim to fame. And of course, every single kind of hot dog has a different spin on it. So one of my favorites is a kimchi Korean style hot dog, bacon wrapped, deep fried, of course. And that's called the Kim Dog Il for the Korean deep fried hot dog. And so, but this food truck though is just one person that does every single part of the job. And this person does every single aspect. He cooks, he cleans, he takes your money, takes your order. So in that kind of architecture, this human-based architecture, everything is synchronous and everything is in process. So this is very similar to an in-tier style architecture. I'm going to call this a monolith, which is a single standalone application where everything in the application is done in process, done by one single thread from the top to the bottom and back up again. And so everything that you could possibly try to accomplish is then code inside this application doing all the work. So in that original food truck, those food trucks are very expensive to operate. Like you have to get licenses for them. You have to actually build this food truck, and those are pretty expensive to do. And so you have to figure like, well, for me to undergo this expensive operation, I need to make sure that my business model makes sense. And so you can basically do the math. If you're just one person, you divide up and count like all the activities that you have to do in order to fulfill an order. And you can just time out how long it takes to do each of those things, and then figure out, okay, what is the total amount of time for an overall order? And then now I can divide on, say, well, what's the number of orders per hour? Then figure out what's the dollars per order. And then now I have a decent idea about how much money I can make in any given day. So I completely made up these numbers. But let's say there are 4 steps. I take the order from the person. I build out I dress out whatever I'm making. I grill whatever I need to do, or deep fry or whatever. And then finally, I pack everything together into a bag, and then I give it to the person that ordered it, and they're done. And so me as a person, I'm standing there for this entire time while all of these steps are completed. So I can figure this out and say, maximum number of orders per hour is 24 times the number of dollars per order, and then have a good idea if this business is even worth doing. But there are some further complications to this model. Because if I find in real life, I never actually achieve that maximum number of orders per hour. I never actually get to 24, and there's a reason why. First of all, people don't actually like to wait in queues. So in the States, maybe in the UK, it's a bit different. You all enjoy waiting in queues, but in the States, we're much more impatient and rude and stuff. And so we don't actually like to wait in a queue for our food. So that means that if I see a long queue, that means people are going to walk away. And I did this. I know I would walk down to the hot dog stand, and if I saw a long queue, I knew that was going to take a long time for me to get my food, but I was hungry. So instead, what I do is I'd order, I see the queue and just whip up my phone and order Uber Eats or something. And maybe that actually would take the same amount of time, but I was going to be standing. It's very hot in the summer in Austin, so it's like 34 to 35 C. So I'm not going to be standing out there waiting in this queue, just looking at my phone in the sun. Not very fun. We also can't assume a constant rate of flow. So even though I might have a maximum throughput of 24 orders per hour, that assumes that basically one person is arriving every 2.5 minutes or so. But in real life, we don't do that. We don't have someone just kind of dribbling and drabbling coming out one at a time at this well-defined interval. Instead, we have peaks and valleys. So we'll have a lot of people show up at once. Maybe they're getting together a group in their company, and they're all walking down as a group. Or we're kind of strange creatures of habit, right? No one eats lunch at 12:17. We eat lunch at on the hour, on the half hour, because something in our brains is wired to say, noon, time to go eat lunch or whatever. So we can't just assume someone's going to show up at these well-defined intervals. And so when someone comes down and sees a long queue, they're just going to be like, I'm not going to wait, and I'm just going to leave. And the person that's actually doing all the work, when they see that long queue, they're going to start to panic, like, oh my gosh, there's so many people, I need some help. So this person, the owner of this food truck, knows that they need to scale their operations in order to be able to meet their demand. Also just probably to be able to make a profit as well. This is very razor thin margin business. So what can they do? They could scale up, but that's not really that feasible, because do they buy a completely new food truck and put it to the side? So we're just gonna have 2 food trucks right next to each other. You don't see that. It's a very expensive setup operation for these things. So really the solution which you see happen here is to try to divide and conquer. And instead of this one person doing every single job, I try to have more people involved in the overall order process, and they collaborate in each of these different steps. So I hire additional workers, and now each person now just does one single job. They're responsible for one activity, one overall step in the value stream process. That also means that once I start to hire additional people, I can have multiple things done in parallel. That is, the grill person and the dress person don't necessarily have to work on one single order at a time. Because they're just dedicated to that single task, they can optimize that task outside of others and say, you know what, we got a big grill here. Why don't I cook 6 hot dogs at once instead of just one at a time? they can start to optimize their own individual operations where they couldn't if everything was done in one single step. And at this point, ordering is now really the true bottleneck in my system here. I can make money as fast as I can successfully take people's orders. And by doing so, instead of me having the max number of orders per hour is like, what, 2.5 minutes per order? In that original picture, I think it had something like ordering took 30 seconds, just completely made up. And if ordering is now my only bottleneck, my theoretical bottleneck for number of orders I can actually fulfill an hour. So my number of orders per hour went from 24, it went fivefold or whatever that is. Yes, fivefold, up to 120 orders per hour as a theoretical max. Now, this looks great on paper. You're like, oh great, we just split up the roles and responsibilities, and we'll have self-organizing teams, and the team will just figure out how to work with each other. But that, in reality, we actually have to plan how these different individuals are going to actually fulfill an order if we want to have a successful experience for the customer. We have to make sure that all the different people know their jobs. They also know how to talk to each other and what the overall flow is to be able to successfully process any individual order. So that becomes our first overall problem, is how do we actually fulfill an order? In our original architecture, the NT architecture, I had one person doing every single job. And that synchronous operation meant that the entire operation was in a single transaction. So when that food truck person took my order, took the money, if he started making the hot dog and it fell on the ground, well, he could just redo the hot dog and do something else again. So that entire operation, I knew that I would not leave the cashier until I had received my hot dog. And that's just kind of the social contract I had with the person fulfilling my orders, that I know that when I start the order, I'm not leaving the spot until I have received my food and I go on with my day. This picture, though, is not like that. In this picture, the only synchronous operation is this initial conversation with taking the order, but the rest of the transaction is no longer synchronous. So I have to figure out, like, how do the later steps in the process know what to do? How do they know what to make? How do we know when we're done? How do I know that I finished completing this individual order? And the solution to this is going to be messaging. So what I'd like to do is look at each of these individual interactions along each step in the process, and then design what is the appropriate communication pattern we want to use for this specific job. So let's look at the first interaction, placing the overall order. So first thing I want to do is look at, okay, what is the information I need from the customer in order to be able to complete this first task? So the information I need from the customer is, what food do you want? So I need to know the food. I need to know how to notify the customer that the order is ready, and we'll get to that here a little bit later. And if you look in real life, this kind of in-person interaction is almost always synchronous. That is, you were talking to another human being, and that other human being is sitting there listening to you give your order, and they're giving you feedback, immediate feedback about how much it costs, and you're giving immediate response to give them your card or do your contact list or whatever it might be. So that means that this first interaction is actually going to be synchronous. The cashier and the customer are blocked during this entire interaction, and this entire interaction does not move on until I've successfully paid for my order. We'll also notice that this initial communication is a non-durable form of communication. That is, the order is requested verbally as opposed to writing it down. So when I go to the front window, I don't write down my order on a piece of paper and then like slide it over to the cashier. I tell them it, and then we can go back and forth very, very quickly. If we try to make this an asynchronous message with a durable form messaging in this picture, it would just be weird, right? Like, you don't write down your order and slide it over. Perhaps something like Uber Eats or something like that, it is an asynchronous durable form of communication. But in the real life, like, I want to have very fast feedback. And if I want to maximize the number of orders I take per hour, I want to have as little latency and overhead for this initial interaction of taking the person's order. So they can tell me the order, I type it down, I say, got your order, here's the amount, they can give it to me, and then they're on send to the side, and I'm moving to the next transaction. As soon as they enter I add additional overhead in terms of communication, then the number of orders I can take starts to go down. So in the virtual world, what would this look like? Well, a synchronous interaction with an immediate response back would just be HTTP. I would choose a synchronous form of communication. So HTTP is a good use for that. Or I could use gRPC if I was an internal kind of system or application. And it's non-durable because there's no one actually writing down the HTTP request anywhere. It's stateless. I give you the post, you accept it, but then it doesn't stay anywhere. I'm really on my own in order to take that information and store it somewhere else. So let's look at some of the patterns used with this initial interaction. This is going to be a synchronous request response interaction. It's synchronous because both sides are blocked and unable to process anything else during this point in time. I mean, in the real world, I guess it could be you're not blocked doing other things. Like I could be on my phone while the person is telling me how much the order costs, but let's just, for simplicity's sake, say that, in real life, this is a synchronous interaction that both parties are blocked from doing any other operation while this interaction is happening. It's request response because I request an order and then they give me a response back saying, I received your order, or thank you for your order, or it's this much money. There's an immediate feedback that me as the recipient on the other side uses that response to say, okay, they have successfully received my order. Now I can go mill about over here in the waiting area. So that was kind of the easy part. What about the next steps, the next interactions? Okay, so I'm the cashier. I received my order. How do I interact with the other people in the process in order to successfully have my order be processed and delivered to the customer at the end of the process? So some of the things I look at, should my interactions be durable or non-durable? Do I write down these messages or just yell them out? Who manages the overall flow? Who manages the steps as they go through the process? And then finally, how do we manage failures? In the initial interaction where it's just one person, failure was very easy to manage because it was that one single person doing all the jobs. And so if that one person messes up, they know how to deal with their own business. They just figure out how to deal with it. In this picture though, we have to explicitly decide how to manage a failure at any one of these overall steps. Because it's not one person managing the entire flow anymore, it's now a distributed system, and there's not necessarily a failure in one single spot. Right, so one place I can point to say this is always going to fail. We don't know upfront exactly where the failures could occur. So what about this first one? Could we do synchronous request response? We could, right? What would this look like in the real life? In real life, this would mean that the cashier synchronously tells the address person what the order is. In the virtual world, this could be something like a REST call or a RPC call. So in the real life, that means like the cashier turning around and yelling the order back out at the address person. And hopefully they're listening and return a response, yep, I got the order. But what if they're busy? They're actually doing other stuff. I yell out the order and I don't receive a response back. So what does that cashier do? They could retry, like a request response with a retry to say like, sounds like your service was unavailable. So let's go ahead and try again. But maybe it's busy again. And then finally, okay, third time's the charm. I yell it out third time. And finally they actually got a response and it says, okay, I got it. Geez, leave me alone. Man, I'm trying to work here. So maybe this can work, maybe not. One of the things we have to worry about with these kind of interactions is if I just say, hey, there's an order, the person could have received that message and then like immediately started trying to process it. And they just forgot to respond back to me. So I have to start to worry about, well, what happens if they receive that order twice? What if I yell out twice and they thought that was 2 orders, but really I was just trying to confirm like, hey, did you hear me the first time? Hey, I got an order up. So the address person has to kind of keep track. Like, was that the same order that person sent me before? Does the dress person now have to keep track of orders it's received? And to be able to know, like, okay, they've yelled at me twice, but if I don't know if it's the same order, I got to go talk to them again to say, oh, was that the same order you just did before? Is this something different? We could also look at something like a fire and forget kind of order, where I don't wait for any kind of confirmation that the dress person is actually doing the work. They just say, yep, I got the order, and then I'll go on and actually fulfill it. So even with just like kind of a simple REST-based API here, we still have to think about all these complications that can occur when I have now two systems not participating in the same individual transaction. That I could have timeouts, I could have services being down, I could have retries, I could receive that same API call multiple times. All of these things can happen now that I've split these two interactions apart from a single transaction, and now I can have these kind of individual overall failures. Now, the second thing we need to figure out is, okay, once we've kind of figured out this first interaction, how do we then flow the order downstream to other folks? And so if I looked at this kind of set of steps in real life, we don't really typically see this kind of like just verbal yelling out. Like when you go to a restaurant, you usually don't hear like a cacophony of yelling behind the scenes of everyone like yelling orders to each other. In fact, if you heard that, you'd probably be pretty worried, like, do they know what they're doing? Because they're just yelling at each other trying to get stuff done. So in real life, it's more of a durable message that flows through each of these different steps in the operation. And we actually have a restaurant here in town that does something very similar to this, in which I have a durable message that flows from step to step to step. And I actually have a picture of it here. So this is a burger place in Texas called Mighty Fine. And one of the interesting things about this place is your order is actually written on the bag that your food is going to be put into at the end of the order. And so what they'll do is they'll circle the things that you ordered, and then that bag will flow through each step in the overall preparation process until the very last thing, when everything's in the bag, they'll say, okay, order up for Vanessa, it looks like, and then they'll give you your food that's in the bag. So in this kind of picture, it's known up front when I place the order, all of the steps that are necessary to be able to process it. And all I need to do is just pass that message from step to step to make sure that the overall process is fulfilled. And this pattern is known as a routing slip, or routing slip, I guess, for the UK folks. And in this pattern, what we'll do is define the message as all the information that's needed to process it, plus a set of steps on that message that describe these are the different receivers of this message to fulfill this order. So in this case, I will send a message to the first step in the process, and that message includes the order information, but also includes all the other steps of the work, so that when the first step finishes, it just needs to look at what is the next step in the process and pass that along to the next step. In that bag we saw earlier, if, for example, I did not want to order French fries, then that bag would not be passed to that next step for fries. It would be passed straight over to the final step, which is to give it to the person to be able to be delivered to me. So if I know these steps up front when I'm placing the order, this is a pretty good pattern, because I don't have to have any kind of central administration or control over the management of this process. The message just flows straight from step to step to step until it finally arrives at the end. The other thing that happens is each individual step manages their own individual backlog of work. So instead of the person in the front yelling orders to the dress person and hoping they're listening and responding back, instead I can just take the order, now it's written down, and I can put that order in that next step's queue. And you'll actually see this physically done in restaurants. You'll either see it virtually, so you'll see like computer screens up above every station that have the orders that are meant for that station. Or you actually see physical queues with like a little slip of paper, your order slip. And that goes to the till that represents the queue for all the different stations. And as each station does its step in the process, it's just working that queue of different orders. It does that order, and then once it's done, it takes that physical slip and then gives it to the next person in the process. So this communication is asynchronous because I'm not directly communicating between each step in the process. It's durable because each individual message is written down. And what this does is it allows to have temporal decoupling. Temporal being that the two operations are not coupled together at a single point in time. So initially when the cashier yelled out at the dress person, those two things had to happen at the same given instance of time for it to happen successfully. But with asynchronous messaging, those can happen at different points in time. I can send a message, keep doing my work, and then sometime in the future, the next step in the process can take the message and actually go on and do its thing. And the final really nice advantage here is that the independence is maintained between each of my steps. Each step can decide how it wants to process and manages the work, how it wants to perform each step in the process. And there's no like rigid set of communication to ensure that everything happens. It's much more loosely coupled here. So this is a very simple flow, but what happens if we turn this up to 11 and try to make things a little bit more interesting? So let's suppose that our restaurant started to become a lot more successful and we wanted to expand it globally and really increase the efficiency and throughput of all of our restaurants. So I wanted to see, well, what do larger chains actually do in order to increase throughput? And kind of the universal chain we could look at is McDonald's. I do admit still to frequenting a McDonald's on occasion. Sometimes it's after I go to the pub, making bad decisions. But at those times it could be pretty delicious. So looking at someone like McDonald's, their orders are a bit more complex. It's not just a simple conveyor belt of flows. When McDonald's actually first started out, there was a great movie a couple years ago starring Michael Keaton that talked about the origination of McDonald's, and it went into some of their original process. And their original restaurant had basically like 3 items on the menu. And so with a very simple menu, they did have just a conveyor belt of how the orders flow through the system. And so it's very much one sequential process where every step was done one at a time. But these days, their orders are quite a bit more complex. Many of the steps are now independent of each other, but some steps are not. Some steps do actually have dependencies. And the biggest complication is now the steps vary per order. Each order can be different, and I need to have a different plan and a different kind of strategy of execution for each individual one. So in the previous one, we relied on the cashier to kind of have an upfront decision about what are the steps that need to happen, which can be done if there's not a lot of complication and a few number of steps. And things become more complicated, especially because I guess they're something like have it your way for a while or something like that. So now we have customizations that can happen. Someone wants their burger well done and they want it cut in half, and someone wants to put fries in their burger or whatever it might be. Like I have a lot more complication introduced in this overall processing. So how do we manage this much more complex process than what we saw earlier? So let's take this step one by one. The first step is actually going to be very, very similar. It's going to be a synchronous process. Although I guess these days they have like those kiosks that we have. Although with like the whole COVID thing, I don't think I would ever touch one of those kiosk things ever again. So probably just do the verbal thing for a while with the mask, of course, I guess. So yeah, we still have an initial synchronous interaction to take your overall order, and nothing really changes there, right? You go up to the person, you tell them your order, they say how much it costs, you give them the money, and it looks exactly the same as we had with the simpler food truck. But what about processing the order? How do we organize all this work behind the scenes to ensure that we maximize throughput, but we minimize our mistakes and kind of maximize customer happiness, I guess? Now, obviously, synchronous is completely untenable here. Like, could you imagine trying to have a synchronous McDonald's? That is, everyone only communicates verbally. I mean, it would be horrible, right? But I see a lot of people approaching their microservices architecture with this exact thought process of like, we're going microservices, so everything has to be REST. Everything's API calls. because Jeff Bezos, before he had $18 trillion, wrote some memo about everything needs an API. But we find like in the real world, everything being asynchronous communication is actually really inefficient. And so that's why you're seeing more and more in the real world, people are trying to be more asynchronous. Like, let's open a ticket, put it in a GitHub issue. Let's communicate via the comments. Let's not have to all get on a Zoom call, to be able to have these kinds of meetings and decisions. So in real world, like trying to do McDonald's just synchronously would just be impossible, and the restaurant would fold within weeks. A routing slip would be too inefficient because the orders are more complicated. And on top of that, some steps can be done in parallel. So there's no dependencies between frying something and grilling something, most of the time. So I can do these things in parallel, but that's really hard to describe in something like a routing slip that I decide up front. So the solution here is going to be a conversation pattern. And conversation patterns are different than communication patterns. And then conversation patterns combines more than one set of communications in order to achieve an overall business objective. So how does McDonald's do it? At McDonald's, actually, the very first step that happens is notification. The person taking the order puts stuff in their computer, and the computer actually notifies all the relevant stations that an order has been created. And inside of that message is the information I need to actually perform whatever step it could be. So instead of me like going one at a time, grill person, do your thing. Okay, grill person's done. Okay, dress person, do your thing. Okay, they're done. Fire person, do your thing. Okay, now they're done. Instead, we notify all the stations all at once about an order coming in, and each station then has their own individual queues they're managing in order to be able to do their own individual work. Now, in the routing slip, it was very easy to track our progress and know kind of where the order was in the overall steps, because the order was only at one step at one point in time. It was at the dress station, then it was at the grill station, and then it was at the prep station, and then it was done. So an order was never split up amongst multiple steps. In this picture though, I can have one order going to like 5 steps at once. I've got these 3 steps, I've got drinks and more drinks, and like a modern McDonald's has like 7 or 8 stations of different jobs that can happen for any one individual order. So now my order is not happening at one station, it's happening at multiple stations all at once. So now the challenge becomes like, how do I know when an order is done? In the routing slips example, it was very easy to know when an order was done, because when it was done with the last step in the assembly line, the order was done. I can give it to the person. In this case, I need to have something that can keep track of which step has been completed. And so how does McDonald's do it? When you go order McDonald's, you may not notice this, but the very first thing they do after they take your order is they put a physical tray down on the counter to hold all the items for your order. And initially that tray is empty except for a receipt. And then on that receipt, the receipt shows what you've ordered. Now the final thing we have to figure out was, how do we coordinate the completion of an order? And that's the whole point of this tray. So when each step completes, the person that completes that step takes the food that they've made and they find the tray that corresponds to that order, and they place the item on that tray. The next thing they do is they look at the tray, look at the food that's on that tray, and then they cross-reference that to the receipt to say, for everything that it's said to put on the tray in the receipt, is everything accounted for on the tray. So they're checking the items on the receipt for doneness. In this case, the person checks the receipt, everything's not on there, and so they say, nope, it's not done yet, so I'll just keep on going. Now, in modern fast food restaurants, that's actually 2 people. One person is doing the work, the other person is actually delivering the food to the tray, so the person doing the work can just focus on doing the work. If you want to think this in terms of virtual terms, you can kind of think of that in terms of one person is the worker taking messages off the queue, while the other person is like a broker or a bus that is delivering the message to something to check for doneness. Okay, the next person does the same thing. The grill person finishes their food, puts the item on the tray, checks the item on the receipt for doneness and says, nope, it's not done yet. They go back and finish their work. The final step in the process, the person frying the French fries takes the food, puts the items on the tray, checks the items on the receipt for doneness, and says, oh, look at that. Everything's on the tray, everything's accounted for. It's time to ship it, give this order to the customer. So this communication pattern has a name, and its name is choreography. I don't like the name a whole lot, but it is what it is. Choreography is this idea of a communication pattern or conversation pattern in which there's not a single person kind of in charge of deciding the overall steps that are going to happen. Instead, all of these steps are happening in parallel, and it's kind of this dance of each individual person doing its own individual thing until the music stops and the dance is done. And so for this one, choreography is primarily defined as event-based initiation. That is, I'm notifying multiple steps in the process to do their own individual work, and that kicks off by some kind of event. Step order is not enforced in this kind of process. When I'm doing a pub-sub event-based model, multiple different services can handle those events simultaneously. And the idea is that there shouldn't be a lot of dependencies between those different steps to ensure that those steps can happen in parallel. But in this kind of process with choreography, something needs to know when the overall process is done. And so with choreography, we have to have some kind of, some manner or mechanism to know like when each individual step is done with this process to know, okay, everything's complete. Now it's time to deliver that order to the customer. So that's really what the tray is about. The tray is a way to keep track of what items have been completed and is kind of a checklist so that once all those items are complete, then I can go ahead and deliver the order to the customer. Years ago, I called this the observer pattern, which I still like better, because it's basically you have something that's observing the events that are occurring, keeping track of which things are done, and when everything's done, then it goes ahead and completes the overall conversation. But we're not quite done, right? All I've done is put all the items on the tray and said, all right, order's done. The last step in the process is, okay, I actually need to give my order to a customer. So how should we accomplish that? I need to have some way of correlating orders with people. Now I could just yell out order up and someone, I guess like everyone just is looking around like, okay, that looks like my order, I'll go ahead and take that. But that probably won't scale very well because people could just take other people's orders. So that's not really what I want. So I need to have some way to tie the order with the person. And there's a couple of different strategies in the real world that people use to correlate those business transactions with the people that initiated those transactions. The first one is with a natural sort of correlation. In this case, a natural correlation would be someone's name. And you see this in some restaurants, like a lot of coffee shops like Starbucks, they write your name in the cup. At the end, they call out your name. So they know that, you know, Jimmy ordered a mocha frappuccino with extra whip, that sort of thing. But sometimes that's not effective because a lot of people can have the same name. So I may need to have something else that differentiates individual orders. So if a natural correlation isn't unique enough within a given set of bounds, then I may have to resort to an artificial correlation. In that case, restaurants use a number. And of course, McDonald's does this. You are assigned a number on your receipt, and they will call you your number at the end. And that also prevents any kind of embarrassing name mispronunciations or name miswriting on the label. So a lot of people use that number because it's a bit easier. So order 53, there we're good to go. Now the downside with the artificial correlation is sometimes people can look a little too into that. So if I'm order 87 and they call it order 15, I'm like, uh-oh, it's gonna be a long time until I get my order. And those also can have problems in the virtual world as well. If I have artificial correlation IDs, I wanna ensure some randomness in there so people don't guess your order numbers or guess your IDs. So the next time you go to McDonald's, which, you know, who knows at this point, or any kind of like fast food, quick service style restaurants, take a look behind the counter and observe how those interactions occur. And you'll see something very similar to this, where you have this initial interaction with this asynchronous transaction, and then you'll have a kind of event that goes out to everyone, and then finally something that kind of pulls everything back together, and that would be choreography. Now, what if we want to go to, instead of like our original hot dog truck, instead of us going the fast food route, like go lower cost, what if we want to get fancy? We have like gourmet deep fried hot dogs. So why don't we look to see how larger kind of sit down restaurants actually work? And one of the things you'll notice about these kinds of restaurants is they're not necessarily trying to optimize for efficiency of processing orders. They're not trying to get you in and out as quickly as possible. What they're really trying to do is get you in there and drink as much as possible. The money's in the alcohol. So they actually don't want to optimize the number of orders an hour. They just want to optimize how long you sit there. That actually is a better measure of their dollars. Is the longer you sit, the more you spend, and the less time they have, the less time they're spending turning tables over and cleaning them. So in these restaurants, orders can be a lot more complex. I could have specials of the day. People can have a lot more requests. They can request things off the menu if they want to. In these cases, timing matters a lot more of individual steps. So in a fast food restaurant, I could say, I'm just gonna cook a bushel of fries because everyone needs fries, so just keep making more and more fries. But in more like fancy pants restaurants, timing matters a lot more to ensure that the person receiving the food has all the food still hot or warm, whatever. So I don't want to cook the steak and have it sit, for 30 minutes while I'm frying the potatoes or something like that. I want to try to time things a little bit better to ensure that I have a very good end result delivered to the customer. So in this case, I need to have a lot more control over the process. I can't just send out a notification and hope for the best, and things are going to kind of trickle back and be received. So there's a good example for this in the real world, and this is more like our good friend here from Kitchen Nightmares. And he is the benevolent dictator that is demanding things from his chefs and kind of dictating exactly when things should be done. So yeah, in this case, we actually have a single person in charge of the overall order that people are making. So in this case, this benevolent dictator, aka the chef, is receiving incoming orders from the waitstaff. They create an overall plan for completion, typically in their head, and they bark orders at different people at different points of time to be able to accomplish this overall goal. I should say, I've only learned this by watching like Kitchen Nightmares, so I don't actually know if this is how restaurants work. I did work in fast food, so I can't vouch for how that worked, but this is just my assumption from watching Gordon Ramsay yell at people a lot. Okay, so the first step in the process is actually very, very similar. We're going to start with an order with the waitstaff. We're going to have a synchronous communication with that person in order to place an order. The difference here is that the waitstaff comes to me. Although in a pub, typically you go to the bar, but whatever. It's still a synchronous interaction. You have a synchronous interaction with the person taking your order, and you tell them what they want, and they'll go off and take it and deliver it to the chef. So I can add stuff to my order, blah, blah, blah. Okay, then it's like, okay, I've got the order, everything's good. Now I got to go take my order and give it to the chef. So during this time, it is a synchronous interaction, and they're confirming that they're receiving my order. But one thing that may be slightly different is I could be getting orders from multiple people. And so what that waitstaff is typically doing is writing down all the things that you're ordering. So it's a synchronous interaction, but they're kind of locally storing what you've ordered with that person until you're ready to say, okay, that's everything. And now they're going to take that and give that to the chef. So the waitstaff tells the chef that the order is ready. So say, okay, order's ready. And this is the ID of the order. Now it's time for the chef to coordinate all the work being done. So they take the order, they look at the items, and they come with that plan in their head of how they're going to get everything that needs to be done. They see that I've ordered a burger. Burgers take a long time, so we want to go ahead and get that started now. So we'll tell the grill person, start making this burger, and here's the details behind the burger. I also ordered a pint. So I'm going to go ahead and tell them to go ahead and at the bar to say, okay, someone ordered a pint with their meal, so we don't have to wait for the overall order to be done. Let's go ahead and say, go ahead and pour the pint. The bar says, pint complete. And now I can say, okay, Waitstaff, put the pint on the counter. It's time to deliver that pint to the customer. And you'll see this in a pub, right? You always get your pint before your food because they want to get your drink as quickly as possible. And so those two steps can happen in parallel. Now, meanwhile, people are making stuff in the background. So I say, okay, now that the burger's down, now I need to tell the fryer to go ahead and start that stuff because it takes a shorter amount of time than the grill. So I wanted to start the grill before the fire so that the burger does not, so the fries don't get cold while the burger is getting grilled. So each step is going to start completing its process. So the grill says, okay, you told me to make the burger, chef, burger's done. The chef is going to wait for the fire to say my fries are done. And now the chef is really the one that's kind of looking at everything to see if everything's done. And finally, once everything is done, it will tell the waitstaff to go ahead and deliver the order, usually by putting the tray of food on the counter with the receipt, and then it goes out and gets delivered to the customer. So this kind of picture, where the previous one was kind of an event-based notifications. In this case, I have one person in charge of coordinating all of the activities. And so this communication pattern is known as orchestration. Orchestration are typically started out by a single message. So a single message kicks off this process. And in our case, the initial message was order created. Order created kicked off the chef to start doing its work. And at that point, the chef was barking orders to individual stations and services to do their work. So the chef uses commands to coordinate subsequent activities. And it uses the request response pattern to indicate completion. So as opposed to sending out a message like Gordon Ramsay did, see like order created, and then everyone does the work, he's telling people to do stuff. And then when those people are done with their stuff, they tell him back, I'm done with this individual step. So those interactions where I'm saying, make the burger, burger done, make the fries, fries done, make the pint, pint done. Each of those are asynchronous and durable, but they are a request response interaction. So in this case, there's actually a lot less tracking of status. Because the chef can manage the flow, he knows in his head, like, I know that I'm going to tell the fire to start his work after the grill is done, so I don't have to keep track of that. I know that the process I've laid out in my head enforces this. And it's not like the fryer is going to get started early, or else I will yell at them even more. So the orchestrator doesn't have to keep track as much as what step has been completed because they're the ones that are controlling the overall flow. So how do we decide between orchestration versus choreography? And this really comes down to analyzing the overall process flow and the coupling between each individual step. And the overall guidance that I give to my teams is that orchestration is usually something that you do inside service boundaries. And the reason why you see it usually inside service boundaries is because orchestration is about telling other people what to do. And if services are supposed to be autonomous, I don't want someone telling me what to do if I'm supposed to be in charge of my own stuff. So in the microservice world, if we want to have services be able to live and run on their own, we don't want to introduce process coupling between service boundaries to be able to accomplish our tasks. We want to preserve the low process coupling between those individual services. And then we have choreography usually between service boundaries because we want to preserve, or we want to reduce process coupling, so other services telling each other what to do. And so we don't have to have services know everything that goes on with every other service. So if we want to change how something works, we don't have to change every single service. Now, this is not a law. This is just a set of guidance that I've found over time tends to encourage good design of service boundaries, but it's definitely not always the case because there are some cases where a service works better using choreography. And a good example of that are technical services. So these are services that aren't really tied to any domain or business bounded context. These are just services that perform a technical function but don't have any actual business logic to them. So in those cases, they don't want to be subscribed to all the different events of the enterprise. They just want to expose an interface that says, if you need me to print something, here's an API. Tell me to print something. The end. So in all this, we've really explored the kind of right side of the equation, that is performing actions, making, like, mutating state, those sort of things. But what about the read side of the equation? Because I tend to find that the read side of the equation, how we compose our services together, looks way, way different than accomplishing business tasks, like the command or right side of the equation. So in the read side of the equation, the way this would manifest in the real world are with catalogs and menus. So the menu gives to the customer that they order off of is a composition of multiple services done in the background. Some characteristics here though, reading the menu is very, very cheap. I don't want to be an expensive operation to see what I'm selling. The menu is purpose-built for the customers in mind, not for the back-end management of this information. And all the decisions on building the menu are not actually visible to the customers. So they don't know how the menu was created. They just see the end result of it. So if I look in the real world, how did this person with this restaurant create this menu? How do they know what ingredients to use? How do they know which suppliers to use? How do they know get to the final step, which is the final, like, amount to charge someone? Well, creating the menu is probably pretty complicated, and someone might use something like Access or Excel to be able to keep track of all these costs and items and supply chain and things like that. And so behind the scenes, these things are really optimized for managing the menu items. It has all the decisions and business rules in them, and has all the calculations and forecasts. So for something like this, if I look at how we typically build systems, we actually use the same thing, the same data storage for the front end as we do with the back end. In the real world, we don't do this, right? We don't give people our Excel spreadsheet as how they're going to order from us. So if you saw this in the real world, you'd be like, really? Excel? So what we're trying to do is we're trying to use the same model to solve two very different problems and very different personas with very different characteristics. And so really, we want two solutions for this. For a system that is interactions and personas that are very read heavy versus personas that are very write heavy, there's going to be very competing, highly competitive concerns over what that data should look like. So a better solution would be something like this, where we have a read optimized store for a set of users that only care about the read, only care about reading information, and then a different data store that's really optimized for the back-end users, for the people that are making business decisions and have all the business rules associated with them. And then the real big question here is then, how do I manage this thing in the middle between the back-end business rules and managing of the data versus the front end? It's the output of the decisions and just reading the information. So in the real world, what does this look like? So I got my business owner here that's got his Excel spreadsheet, and what they'll do is they'll probably update the menu on a very scheduled basis. So typically, daily or weekly, even monthly perhaps. But it's not intended to be kind of real time necessarily. Like it's not meant to be like the millisecond that the business owner makes a decision that magically the menu updates and all the prices get updated. Because honestly, as a consumer, that'd be very disconcerting to be standing in queue, looking at the menu and seeing the price change right before you. Be like, what? I mean, the price went down, probably happy. Price goes up, you're not happy and you're probably leaving. Some other characteristics here is the menu is immutable. That is, no one inside the store can change that menu. It's not like one day the manager's like, you know what? I think burgers should be 3 pounds, not 2 pounds, and just like crosses it over and makes it 3 pounds. No, there's someone else that makes the decision. They are just receiving the outcome of the decision, and they can't change those results of the decision. So in this case, even though the data is, quote, duplicated, ownership of that data is still preserved. So there's a copy of the data of that owner's spreadsheet in the printed menu at the pub. So the data is technically duplicated. However, the owner of that pub still owns the price and list of the menu. So as long as ownership is preserved, that data can be copied and replicated and shared amongst people that need it. So in the real world, how can this look like? We could use, again, publishing of messages to say, hey, I've got a new menu for you folks. Here's the date the menu is supposed to go into effect. And here's the items and the price of things on that menu. In the real world, this could just be like an email with an attachment, I guess, as the event that flows through to the person receiving it. And we could have multiple subscribers of that message as well. So the publisher is keeping track of all the different subscribers to the menu information by the number of stores. It's durable in format because I want to make sure that the stores can process it on their own time and not like as soon as as soon as out of the words, it's been updated. And when I publish, I actually create a distinct message per individual consumer or subscriber. So I send an email out with the attachment. Here's the new prices. And store A, store B, store C, all each get individual copies. So in this case, I'm going to get a durable message to each individual subscriber. Each subscriber is wholly unaware of the other. So store A and store B are not coupled to each other about exactly, they're not colluding to say when we're going to put these new prices into effect. They don't really have any knowledge of each other. And finally, if one of the subscribers closed or goes out of business or didn't check their email that week, the other stores and other places continue to operate as normal, perhaps with slightly updated data than the others. And this is a business decision we have to make. Like, is it okay if one of the receivers of the information doesn't process it at the exact same time as someone else? Is that okay? And in the real world, we find that that generally is okay. Like, no one is running from store to store to check the prices to make sure everything is 100% in effect at all at the same time. Or we'll do something like we'll publish out the pricing sheets ahead of time with an effective date to give stores plenty of time to get ready to be able to put those prices into effect. So even though we don't have like a single source of central truth here, the world still continues to operate and function without having to go to some central store, some central database to be able to get, 100% up-to-date prices at every point in time. It's just not tenable, honestly not something that the stores want to do in the first place. So I want to give some parting thoughts. When I look at how people make mistakes in distributed systems, a lot of times it's because they're building systems that would never work in real life. If I imagine every single service and system as a human performing a task, if it would not work in the real world, it almost certainly won't work in the virtual world. So that's what I find is the fallacy of distributed computing are still very much in play. Constraints of the real world really haven't changed. It's just the latency has gotten shorter, but latency is still not zero. There's still going to be a delay between each interaction. A lot of the solutions that we see in the real world that people have figured out over the centuries and millennia, those solutions can be interpreted and applied as patterns directly to a distributed world. And since the real world solved a lot of these distribution problems with messaging and conversation coordination, all really it takes for us is to define and recognize those patterns and apply them based on the constraints that we actually have. Yeah, it's okay to do. So that was all I have. You can find, again, this presentation on my GitHub at github.com/jbogard. There's a presentations repository there with all the information on it. Otherwise, I think we do have some time for some questions, I think.